The lathe was the first machine tool that was ever built with a rotating spindle. It's rather interesting to look at the pictures of some of the old machines, because they were actually made as spring pole machines, which means that a sapling was cantilevered out with a rope from it, and the rope was wrapped around the workpiece, and in some way the operator would push his foot up and down and power the lathe. Of course, this predated any sort of steam engine, gas engine, or electric motor. Must have been difficult working that way. In 1797, it's recorded that Maudsley was the first person to build a lathe in which he used gears between the spindle and the lead screw. So effectively, he had made the first screw-cutting lathe, which opened many doors. It made possible doing accurate work. And really, this was a very important part of the Industrial Revolution, because for the first time, people were able to produce accurate parts for machines, for engines, and this spurred the development of machines and engines. The lathe, being the first machine tool with a rotating spindle, turned off a whole series of other machines. After people had worked on a lathe for a while, in which the workpiece rotated and was presented against a more or less stationary tool, the idea occurred to someone that they could rotate the tool and move the workpiece. And of course, this is the condition that you have in a horizontal milling machine. So the first outgrowth of the lathe was the development of the horizontal milling machine. And I guess it wasn't too long before people got the idea that they could turn the spindle into a vertical position and have a vertical milling machine, and also a drill press. So the lathe led the way into a whole series of machine tools that we use today and take for granted. Since the lathe has the rotating spindle, which is connected to the lead screw, it can do virtually any job that another machine tool can do. The lathe is a little bit restricted in doing the work because the way the platforms are made for moving the tool on the lathe, you have only a limited amount of movement. Clearly, if you're using the cross slide of a lathe for milling operations, you don't have the nice amount of table space that you do on a milling machine, and you don't have as much movement. But you can do milling cuts, you can do drilling cuts, and these are some of the aspects of advanced lathe work that we're going to get into today. What I would like to emphasize is the fact that we can do very accurate work on a lathe. The modern lathes are built with a great deal of accuracy built into them, and there are ways that we can take the greatest advantage of it, and in fact, we can extend the accuracy of the work that we produce on any lathe beyond what is built into the lathe. Sometimes I say that to someone and they look at me with their eyebrows raised as though, what are you talking about? But think about it logically. There is no great master lathe somewhere that turns out all of the other lathes and they get more and more accurate. People are working on whatever they have. And by using good machining techniques and good setup techniques, they extend the accuracy of the work that they're doing beyond what the lathe is capable of upon which they're working. So that a man beginning with whatever the lathe happens to be for accuracy is able to produce a better lathe or a better milling machine, and from that he produces better. That the machinery we have today is quite good. That if you can do nothing more than obtain the accuracy that's built into your lathe, you will be producing very good work. And if you consider things very carefully, think about what you're doing, think the whole process through, you'll find that doing the lathe work and other work becomes much more interesting to you. And you may get some very pleasant surprises in what you can turn out. As you get into evaluating your machine and examining it and considering how to do things, you may get some other surprises. Sometimes they're not so good. But we're going to show you today how to make a test bar so that you can evaluate your lathe, so that you can move things into position and get them accurate, and do it with a minimal amount of time and with a maximum amount of accuracy. Now, there's a great deal of accuracy built into the lathe, and when you want to turn something which is to be a cylindrical shape, it's obvious that you have to have the tailstock and the headstock accurately aligned with one another. You have to determine that the axis of the lathe, which is the axis of rotation, is exactly parallel to the ways of the lathe, so that as your tool moves, its movement is parallel with the center of rotation of the workpiece. You must always remember that the headstock of the lathe is the fixed point from which you work. There's no way that you can adjust the position. If you begin to try to do something with adjusting the position of the headstock, you're likely to get into a lot of trouble. You can adjust the tailstock. The tailstock is made to be adjustable, and it should be used so that you can determine exactly where the axis of rotation is, so that you can turn true cylindrical workpieces, or if you wish to offset the axis of the lathe in order to turn a taper, it's done through the tailstock. Now the place where we begin is right here on the tailstock. Every lathe that has tailstock set over provision has some kind of a witnessing mark on the heel of the tailstock. This is only an approximate mark. If you try to work from this and set this as accurately as you can by eye and put a workpiece in and turn it, there's a very good chance that you're going to find that it's turning a taper. If you have a workpiece of, say, 10 or 12 inch length, and you run your tool and turn it, you may find that one end is larger in diameter than the other, which indicates that your tailstock is not properly aligned to the headstock. So what we want to get into today for the first thing is to determine exactly where this tailstock should be so that it lines up exactly with the headstock. This will permit you to turn accurate cylindrical work to begin with, or if you wish to set it over, it will allow you to machine a taper which is exactly the dimensions that you want. And we're also going to get into checking the position of the compound slide so that you can machine short parallel cylinders, or you can machine short tapers by using the compound slide. But you begin by setting the machine, as I have done here, with the witness marks approximately in line with one another. The way that you set this is by using two screws which are in the base. And you'll notice that I'm loosening them both. Now I'm not able to tell you which way you must do this on your particular lathe, because every lathe is made differently. It's up to the manufacturer. But you see, as I tighten that screw, you can see that this witness mark has moved. So this is where I begin my operation, by loosening up these screws and adjusting the tailstock position as accurately as I can to bring the witness marks in line with one another. As I'm tightening that up, it's moving back. You see the tailstock is moving across in that direction. It's moving away from me. And I'm bringing it in. And at that point I have the witness marks right about in line with one another. So I tighten the screw on the opposite side. And that's about as much as I can do with setting that to begin with. Now it will be reasonably accurate, but it will not be dead accurate the way we're going to have it in a few minutes. The first thing that we have to do is to make a test bar, which we're going to set up on centers, and we're going to use that to determine the exact degree that we want. In order to make the first test bar, you should cut off a piece of round steel rod. I use 1 inch diameter. That's a very convenient size. And you're going to want about a 10-inch length. And we're going to go through the machining steps and show you how to set that up. The thing that you're going to need to make your test bar is to set it up so that you can accurately machine the ends. The best way to do that is to support one end of the test bar in your 3-jaw chuck while you support the other end in your 3-point steady rest. As you put the steady rest in position, wipe the ways a little bit to be sure that there are no chips under it, because you want everything to sit as solidly and as straight as possible. You'll need a tool on the tool post with which you can take a facing cut and with which you can take a turning cut. And you'll need the tailstock drill chuck with a medium-sized center drill in it. What you're going to need to make your test bar, in addition to the short piece of steel rod, is that you should set up the 3-jaw chuck on the headstock of the lathe, and you should put your fixed steady rest in place. When you put the fixed steady rest in place, wipe the ways to be sure you have no chips or anything under it. This will help to promote accuracy. You'll want a tool on the tool rest, which will be used for both a turning cut and for a facing cut. You'll begin with a facing cut, and you will also want to be using the tailstock drill chuck with a medium-sized center drill in place. Now I'm going to put the test bar into place, bringing it into the chuck, and then tightening the chuck jaws. At this point it should rotate nicely as I pull it over by hand, and it does. We have everything in good alignment. You have to be careful with the 3-point steady because you want this all to be on the axis of the lathe. You want the rotation to be as nearly perfect as you can get it. Since you haven't checked your lathe out yet, it's possible that you'll be off a little, but try to bring it as close as you can. At this point we can bring all of the jaws of the steady rest into contact with the workpiece, and now it's ready to begin the machining operation. Advance the tool into the end of the work so that you can make a facing cut. Cut from the center out. I'm just barely bringing the tool into contact with the work at the present time. I'm removing a little bit because the end had been saw cut, so it was really quite uneven. In fact, it was a little more uneven than I realized. I'm going to put a little cutting oil on that because it cuts better when the work has an oil to cool the tool. We're getting a uniform chip lifting off, so the work is coming along okay. Now I have a continuous machined surface on the end of the workpiece, which I know is square because I just machined it. So I can move the carriage out of the way. And bring up the tailstock drill chuck with a center drill in it. Now I can slowly begin to drill the center away. We want to drill a good solid pocket in the end so that we can support the end of the bar on the lathe center, and we want enough of a reserve in there to hold the lubricant while we're running it. This lathe is fairly well aligned because I've aligned it in the past. I just moved it, as you saw when I was showing you how the tailstock sit-over goes, but I've been running this lathe for so many years and I know it so well that without any further checking I have it quite close to being exactly on. The test bar that we're making here is really a tool in its own right. It's a useful accessory that you will protect and put away, and you will always have it to use for your own machine. And if a good friend of yours down the street tells you, I can't get my lathe lined up, you can take it down and do it for him in a matter of a few minutes, and he'll probably be your friend forever. The center drill is cutting in very nicely now. We're up to the tapered part. Don't cut in too far because you don't want to get into the parallel part of the center drill. That will ruin the accuracy of the end. You want a tapered entrance hole. Now that completes the machining on the first end. I'd like you to take the bar out of the lathe and reverse it, and repeat the same procedure on the opposite end. Then you'll have both ends of your test bar machined off straight and at right angles to the bar, and you will have both ends of the test bar center drilled so that you can do further work with it. There is the way the end of the bar should look. And you will want both of the ends to be machined in the same way. Now for the next step in making your test bar, you're going to want to do a turning cut in the lathe. So you should begin by putting on a catch plate in order to drive the work, because we're going to work between centers. That's the most accurate way that we can handle making the test bar. Put the catch plate on the headstock and put in a dead center. Put a center in the tailstock, a live center if you use them, or a dead center. It's the type that I use here. Now I've prepared the workpiece just as we've shown and discussed. Each end has been faced off and center drilled. In addition, I've attached a lathe dog to one end so that I can mount this workpiece between centers. Don't forget to put some lubricant in the end that's going to be running on the tail, because that center will not be rotating. Now the lathe is set up, and we're all prepared to take a turning cut on this end. The turning cut we're going to take is going to be a short one, only about 1/2 of an inch or so, and there's no need to work to any specific diameter. Whatever diameter you turn will be fine. You don't have to remove a lot of metal. If you take away 10 or 15 thousandths of an inch, that will be just fine. I have the workpiece set up now between centers for turning. I'm driving it with a lathe dog from the catch plate. And I want to take a short turning cut on this tailstock end. I'm going to cut for about 1/2 of an inch, and I'm going to remove 10 or 15 thousandths of an inch. The exact diameter is not important. I recommend that you put your lathe on automatic feed for taking the cut, so that you will have as smooth a job as you can possibly get. See, the tool is just beginning to lift a light chip from the workpiece now. And that's exactly what we want. It's cutting all the way around, and it's going to leave a nice, freshly machined surface. point in machining this half-inch piece is that this is going to give you a very accurate surface which you can touch with your indicator when you're using this as a test bar. Now that the turning cut is completed, you can remove the test bar from the lathe. And there's the way the end should look. You see it has a nicely turned shoulder, which is very accurate because we've just turned it between centers. And it has the accurate center drilled spots on both ends so that we can mount it between centers. The length of the test bar is not critical. I've chosen 10 inches as a convenient size because I'm working on an 18-inch lathe. And if I am able to place everything accurate within a half a thousandth of an inch or so over a 10-inch span, I really have the lathe pretty accurately aligned. If you're working on a different size lathe, you may wish to use a different length for your test bar. If you're working on a long bed lathe, you could increase the length to 12 or 14 inches if you want. I really don't think it's necessary to go beyond 12 inches even on a long lathe. If you happen to be working on a short bed lathe, you may wish to reduce the length. And I would be a little bit skeptical about going below 6 inches because that's getting to be a little bit too short. But this is the way you've made your test bar. It's an accurate piece. It's as good as your micrometer. And it's something that you should protect and put away. You can use it on this lathe on which you made it, or you can use it on any other lathe in which it will fit. So we're going to go on now and put this piece of tooling to work. When you begin to set your lathe up to do very accurate work, I recommend that you have an indicator. The one that we're going to be using here is a standard indicator. It's calibrated in thousandths of an inch, and it has a 1-inch travel. If you have an indicator which has a smaller travel than that, for example, a 1/2 inch or a 1/4 inch, that's fine for this job. In fact, if you have one of the little centering indicators which goes 10 or 15 thousandths of an inch each side of center, you will be able to use that. As we get into doing tapering work, an indicator which has a little greater travel is more convenient to use. I have an indicator mounting here which I made for the lathe also. You'll notice that it has a clamping piece at the bottom, and it's simply made so that I can insert the indicator in the hole and I can lock it in place by this knurled thumb screw. I made this in the shop because I made this especially for my South Bend lathe. The hole that I drilled for mounting the indicator is exactly on the lathe axis. In other words, I measured from the top of my compound rest where this tool is mounted, so that from this bottom surface to the center height of where the hole is drilled for the indicator coincides exactly with the center height of the lathe above the top surface of the compound rest. So I can slip this into place and tighten it down, and we're ready to begin making some measurements. It doesn't have to be tightened down extremely hard, but you want it to be tight enough that it's not going to move under anything that you apply to it. Now I'm going to tip this over into a position where you'll be able to watch the hand on the indicator so that you can see exactly what I'm doing. With the indicator in place, I'm ready to put my test bar in between the lathe centers. Be sure that it's mounted firmly, and notice one thing. As I put this between lathe centers, the part that we turned very accurately, I have turned toward the headstock of the lathe. There's an important reason for doing this. You'll remember that we said the headstock of the lathe is built in essentially a fixed position, and you don't want to be moving that or working around with it. So this means that this becomes our reference point. And this is the way that we will begin, by putting our test bar in place so that we can take a reference reading from this machined surface at the head end of the lathe. Now as I run this in, I'm bringing the contact point of the indicator against the work surface. And you can see the position that this is, that my indicator is centered exactly on the center height of the lathe. So whatever readings I'm taking are directly from the center of the lathe. I run the cross slide in far enough to give a deflection of the needle, which is a good solid reading, and then I turn the bezel so that I get a 0 mark on the needle. Now, at this point, I don't want to move anything. If you want to, you can tighten the gibs and lock your cross slide in that position. I have them set up fairly firmly, so I'm not going to lock them. I'm going to let it sit in this position because I know that the cross slide will not move. Now I can loosen the test bar, and as I do, I pull back on the indicator. The indicator has a knurled ring at the top, and I reverse the bar end for end, and I let the indicator contact go back in. Now, without moving the cross slide, I pull the indicator back so that it doesn't contact the bar, and I run the carriage to the opposite end. When I get in position over the machined area on the test bar, I let the contact go back against it. Now you see what I've done. This center point and this center point are defining where the axis of the lathe is at the present time. When I took my indicator reading at this end, I measured an exact distance from the center axis of the lathe. By reversing the bar, I've moved that exact distance down to the tail end, and as I let the indicator point come in contact with it, I am measuring the exact distance from the axis. In other words, I have defined where the axis is. If my indicator reading is still 0 when I take it at this end, I know that I have this axis exactly in line with the ways of the lathe, because this is where the carriage traveled. If I have some deviation from a 0 reading, I know that the axis is offset in one way or the other, and I will correct that by using the set-over screws as I showed you before when we made the rough alignment. Now as I check this, I find that I have about a 5/1000th of an inch deflection showing on the indicator, which means that I have to move the tailstock by approximately 5/1000ths of an inch. Leaving the indicator in contact with the workpiece, I loosen each of the set screws that are used for adjusting the tailstock, and now I make a shift in the tailstock by tightening one side. I have to loosen the hold down bolt. I made it just a little bit too tight. This hold down bolt, you see, passes right through the entire base of the tailstock, and by making it too tight, I've made it too difficult for me to shift the set-over setting. So I'm putting this back into position. Now as I move this, you see, as I do it in this direction, I'm getting the offset worse and worse. You see the deflection is increasing. But as I tighten from this side, I will be able to shift it back. I have to loosen this side a little bit. You can see that the needle is coming back, and I bring it back until it's exactly on the 0 position. When my indicator shows exactly 0, I know now that I have moved the tailstock over so that it's exactly in line with the headstock. When I get the exact position that I need, I tighten the opposite screw, and my lathe is aligned. That's all there is to it. At this point, I know that I have made the situation in which the center line of the lathe traveling from the tailstock to the headstock is exactly uniform with respect to the ways of the lathe, and I should be able to turn a perfectly cylindrical workpiece. That's a very quick, easy adjustment. Now what happens if you set up and you begin to work and you find that your work is not cylindrical? In other words, that you're machining some kind of a taper. The first thing that you do is reverse the bar, put it in at the headstock, the turned end, repeat this entire check that we did, reverse it so you're measuring and determine what has happened. If everything still looks in line, there's another step that you have to complete, and we're going to show you how to do that also. All right, now we're considering the hypothetical case in which you may find that your lathe is in very bad alignment. You've gone through the work with a test bar, checking to get the tailstock set over to match against the headstock, and you find that it still turns tapers on you, so what to do? The next thing to do is to consider whether the axis of the lathe is truly horizontal and parallel to the ways in the horizontal plane. You still use your same test bar to check that, but the check has to be done in the vertical position. I've mounted an indicator on the compound slide so that it's sensing vertically, and as I run this in, you'll see that I get a deflection on the needle, in which it increases and it increases and it increases, and at a certain point it begins to decrease. The point that you want to feel for is the maximum point, which is right about there. That means that you're exactly over the lathe axis, and you're measuring in a vertical direction the distance between the machined surface on your test bar and the lathe axis. When you find that point, change the collar on your indicator so that you record it as a 0 point. Then you can back the cross slide off. Now once again, you can reverse your test bar so that you can repeat this measurement at the tail end of the lathe without changing the position of the cross slide. Run the carriage back, feed the cross slide in, work it across, and you see that you come to some reading. Now the reading that I'm coming to here is a couple of thousandths below the reading that I had at this end. This tells me that my tailstock is sitting a little bit too low. The only way that I can correct that is by inserting shims. There are two bearing surfaces in the tailstock, one at the back end and one at the front end, and I will have to insert a shim in each one so that I raise the complete tailstock. Now, this may get to be a frustrating job, and if you begin to feel aggravated, take a walk for a little while and come back. You see what happens? This point where you're measuring is quite far out from this one, which means that there is an amplification factor. If you put a shim in here, as we read here, about 3 or 4 thousandths, you think you should insert a 3 or 4 thousandth shim, should bring everything up, it should be fine. You may find that it's not, because you may find that because of the amplification in the tip of this tailstock, that you will actually get a reading where it will move out by 7 or 8 thousandths. And you have to go back and forth and work until you get that exactly at the same height. But you can go back and check your reference end, and you can come down here and you can check as we've done here. And each time you do it, you should be able to get closer and closer. Take your time and get it so that this plane is exactly parallel to the lathe ways. This function is just as important as the tailstock set over, because when your lathe tool is set to be exactly on the lathe axis, if this happens to be inclined, whether it be tipped up or whether it be tipped down, as your tool cuts, it's going to be farther away from the center at this end than it is at this end, which means that your work will always be larger at the tailstock end if there's something wrong with the height adjustment of your tailstock. So this is one of the things that you want to work for. Work to get the tailstock set over exactly right so that you have the axis parallel to the ways. Work to get the tailstock height exactly right so that the lathe axis is exactly parallel to the ways. The headstock is your reference. All adjustments must be made in the tailstock. When you're doing automatic feed work on the lathe where you're taking long turning cuts, it's normal for the cut to be taken by the movement of the carriage along the ways. But there are many times when you're wanting to turn short cylindrical sections on mandrels or little stubs or little crank pins or things of that sort, in which you don't use the movement of the carriage because they're short and you prefer to turn them by using the compound slide. Now, the question comes up of how do you align the compound slide accurately so that you get a perfectly cylindrical workpiece. This question is similar to how do you get the axis lined up so that when you move the carriage you get a perfectly cylindrical piece. However, you have now reached the point where you have done the alignment work and you have your lathe accurately aligned. So, how do we approach it? What I suggest is that you make a short test bar like this one. It's made in a way very similar to the way you made the long one. The ends are center drilled and faced off, both ends, so that it can be mounted between centers. But now that you have your centers aligned and you're able to turn a true cylinder by moving the carriage, you turn down a part like this, which is 3 inches long, 4 inches long, 3 inches is usually about enough, so that you can put this between lathe centers, and this again becomes a short test bar. You check the alignment of your lathe by taking a turning cut after you've put this between centers. With your micrometer, you check the diameter in 2 or 3 different places. If they agree with no difference in their diameter, you have a very fine test bar to use. If you find that there's a little variation, maybe a 0.5 or so, and you want it more accurately than that, you go back and you take a second cut. If necessary, you change the set over position on your tailstock a little bit. But once you've made it, both ends faced off, both ends center drilled, a 3 or 4 inch area accurately turned so it's exactly the same diameter throughout its length, you can put this in place between the centers of the lathe, and you have another test bar to work with. Now this test bar is going to be used so that we position this compound slide. As it sits, it has a scale reading around the base, and it has an indicator mark on each side, an index. And by loosening the clamping screws, I can turn the compound slide to any position that I want. The most useful position is when it's parallel to the lathe axis, because that allows me to make the short, straight turning that I've spoken of. When I bring this into position so that the index mark aligns with the 0, theoretically it's parallel to the lathe axis. And if you're doing rough work, it's probably okay. But the chances are that it's not really where you want it, because when you're reading these marks, they're rather coarse, and you can be off by some fraction of a degree, I don't know how much, depending upon the width of the line and how good your eyesight is, I suppose. But it will not be dead parallel. So I'm going to use the indicator which I was using before with this little mounting that I've made, and I'm going to put it in position on the compound slide just as I did before. This goes into position so that I'm taking my measurement exactly on the center height of the lathe, and I tighten it into position slightly. And I bring the carriage back so it's in about its mid position, and I run this in until I get some solid reading. And once again I turn the bezel of the instrument to set the zero. Now as I move the compound slide from end to end of its travel, you'll see that I'm getting a deflection of the indicator needle. Now this illustrates what I just was speaking about. I've set this compound slide just as accurately as I can from the protractor marks on the base, but it's really quite a ways off. Within 2 inches of travel or so, I'm getting a deflection of about 0.08 of an inch. So what I do at that point is to loosen the screws that hold the compound rest in position. And I turn the compound rest to a new position. As I do it, I'll have to back the cross slide out. I'm moving everything here because I didn't tighten it enough. I'll tighten this down just a little bit more so that it doesn't shift on me. Now I recheck. Whoops, I moved it. That's not good. I should tighten this just a little farther. All right. Now as I move it from end to end, I'm getting a little less deflection than I had before. So I can gently shift the compound slide, and we're close, so I think just a little gentle tap here is probably enough. Notice that the hammer that I'm using is a rawhide hammer so that I don't scar anything. And I have to make a shift from side to side. This is another place where the movement is not directly read because there is an amplification factor, because where the pivot is located is closer to one end than the other. So I just make a gentle shifting of the piece, and you can see that the deflection is getting less each time I do that. I'm shifting the compound slide into position so that it will be parallel. Now I moved it a little too far that time. It's a case of shifting back and forth from end to end until you get it exactly where you want it. And some of these jobs can be just a bit frustrating sometimes because it seems as though you're getting there and suddenly you've gone way too far, which is what I've done now. It may take several passes to get the position exactly parallel. Sometimes when you're going after the last bit of accuracy, it can really be quite aggravating. But this is a question which is like purity. The finer you get it, the more difficult it is to achieve. As you can see right now, we have very little deflection, and we keep going until we have it exactly where we want it. After several tries, you can see that I have the indicator with no deflection whatever as I move the compound slide from end to end on its travel. At that point, I tighten down on the screws that lock it in position, and it's ready to go to work. There's a little aggravation sometimes in working toward that last shred of accuracy, but it's worth doing it if you really want to produce accurate work. Notice that the hammer that I've been using for tapping on the lathe in different places is a rawhide mallet. It has a soft head. It doesn't weigh very much. I'm tapping very lightly, but it allows me to move things that very small amount. Now that we've gone through the procedure for getting the lathe all lined up exactly parallel to the ways, you will be in a condition where you can machine nice, straight, cylindrical pieces. But suppose you want to machine a deliberate taper. For example, the centers that go in your lathe have taper shanks on them, which are tapered to a certain degree. They're Morse tapers. There are brown and sharp tapers, and there are other forms of tapers that you may wish to make, or you may simply wish to make a tapered piece for some other reason. How do you proceed to adjust your lathe for making a taper? Well, this is a place where your little test bar comes in handy once again, because we know now at the present moment that this lathe is all set. So if I put the test bar into position, I know that I have my lathe set straight. And if I run the carriage back, and I feed the compound rest in with the cross feed, I can bring it into the point where I get a good zero reading. Now, without moving the cross slide, I can once again displace the tailstock by using the set over adjustment and move it to a certain degree, whatever I happen to need for my set over. For instance, if I'm wanting to machine a Morse taper, I may need a set over of 30/1000 of an inch. All I have to do is loosen the screws in the tailstock, and now as I make the adjustment, I can move the tailstock over, and there I've moved it exactly 30/1000 of an inch. Once I get it moved to the point where I want it, I tighten the screw on the opposite side, and the lathe is set now to machine a taper which will be 30/1000 of an inch smaller on this end of the workpiece than it is on this end. Or if I move the tailstock set over in the opposite direction, I can make it so that this end will be larger than this end. When the tailstock is moved toward the rear of the lathe, this end will be larger than this end. When the tailstock is set over toward the front of the lathe, this end will be smaller than this end. So now I have a means of getting the lathe exactly in line to cut cylinders. I have a means of getting the lathe exactly in line so that I can machine standard tapers to whatever degree that I want. By using the indicator, you get an exact measurement of how far you set the tail over. You know exactly how much taper you're putting into it, and you know exactly how to return the lathe to its zero position. You see, if I have machined a taper and now I want to come back, all I have to do is loosen the screws, and as I make the adjustment on the tailstock set over screw, you see I'm returning the tailstock to its initial position. There it is, right back on the zero. Now as I tighten the screw on the opposite side, I've returned the lathe to its zero position. So by making this simple test bar, making a little mounting for your indicator, you can achieve a high degree of accuracy in the position of the workpiece on your lathe with a minimum of effort. It's easy to do, it's quick to do, and it's accurate, and that's what counts. Now that we have the lathe accurately lined up so that its movements are all accurate, we know that the carriage is moving parallel to the axis of the lathe. We've adjusted the compound slide so we know that it's moving parallel to the axis of the lathe. We're prepared to begin to do some other work which also calls for accuracy. I'm referring to thread cutting. By changing the gears on the headstock of the lathe, it's possible to cut fairly large threads, whether they be external threads or internal threads. This topic is one that we have covered already in another videotape in this series. What I'd like to talk about now is how to cut the small threads and show you the procedure for machining small external threads and small internal threads. I'm holding in my hand a piece of work which is a steel rod. It's going to be an axle, and I believe you can see that on this end I've already machined a shoulder down and I've cut a thread on it. The workpiece calls for a similar job to be done on the opposite end. So I'm going to put this in a collet in the lathe. I'm going to take a facing cut across the end, and I'm going to turn down the area that's necessary for cutting a 1032 thread, and we will put that thread on using a tailstock die holder. When I mount the workpiece in the collet, I allow just enough to hang out to take care of the work that I'm going to do. And I'm going to take my cut using the compound slide because I know that I have this straight, and I'll machine a nice straight little shoulder there using it. I'm running the lathe fairly quickly because this is a small piece of steel that I'm working on. And the first thing I'll do is take a truing cut, and I put a little cutting oil on the end of the rod. In this case, the length of the thread is not critical because the part of the rod that we're going to turn down is going to stick through another workpiece, and a nut will go on the outside. So we have to cut enough thread to hold the nut, but we have to have a little bit longer shoulder. We're going to cut a shoulder about 1/2 inch long. And I put a little cutting oil on the outside of the work. And as I feed the compound slide forward, I note where it begins to contact the workpiece, and I continue to machine because I'm going to go for a 1/2 inch depth. turned a full ½ inch shoulder, but of course it's still oversized. We're going to put a 1032 thread on it, which is about 3/16 of an inch in diameter. So I'll gradually turn the shoulder down. Now I still have a ways to go, but it's time for me to check with a micrometer so I know how much to take off on the next pass. It measures 258 thousandths, which means we have to remove about 70 thousandths more. Alright, we have the diameter just right for cutting the thread now. Once the part that has to have the thread put on it has been reduced to the correct diameter, you're ready to start the thread with a tailstock die holder. This is a little die holder which I made for the lathe. It has a number 2 Morse taper so that it goes right into the tailstock, and in the front end it has a set screw so that I can put a die in and lock it in place. So I put the tailstock die holder in place, I insert the die, and of course dies have one side where they start better than the other, so you observe that and put the die in. And tighten it in place securely. Now I don't use power when I'm doing this part of the operation. I do this by hand. And I put a little cutting oil on the part of the shoulder where the thread will be cut. And I move the tailstock up into position. This is a two-handed job. And I am going to turn the machine over by hand by turning the pulley back on the counter shaft. Now when I do this operation, I don't like it to turn too fast, so I disengage the pin in the bull wheel and I engage the back gears so that the spindle turns over slowly, and this gives me a good control over what's going on. With my right hand I bring the die up so it's beginning to engage the end of the workpiece, and I begin turning the counter shaft pulley. With my left hand and with my right hand I keep advancing the ram on the tailstock, and as I do, the die begins to cut the thread. Now the spindle is turning very slowly because I have it in back gear. It makes it very easy for me to keep up with the progress with my right hand as I'm advancing it. And I keep doing this until I have the thread very well started. With everything being in line, I can be sure that that thread is starting accurately and that it's going to be a true thread. Once I've run the thread in a considerable distance, I can free the tailstock from the lathe bed. Now I don't have to feed anymore because the tailstock is free to move. It's still holding the die in its accurate position, but I don't have to hold against it any longer. Now I can continue to run the thread up, or I can withdraw the tailstock completely, and I can run the die the rest of the way using a die holder. If I want to do that, all I have to do is free the set screw that holds the die, back the tailstock off, and remove the tailstock die holder. You can see the die is in place now. We've cut several threads, and it's nicely started. Now I can change over to a hand held die stock and finish the thread by hand. Once I have it all cut to the depth that I want, all I have to do is back it off, and at this point it's probably loose enough that I can remove the die by hand. I'm not sure. We'll try it. There it is, and you can see I've machined a nice thread on the tip of that shaft, and you can depend upon that thread to be accurate in line with the rest of the work. We can do a similar procedure for cutting an internal thread, and I'm going to set up another workpiece in a moment to show you how I do that using a tap. It's important when you're doing accurate work on the lathe that you always face off the end of the work before you begin to do any other operation. Whether you're cutting an external thread as we just did on the shoulder, or whether you're cutting an internal thread as we're going to do now, the thread we're going to cut has to be cut into the end of this rod, which I have running in the collet, which is the most accurate way I can mount the work. And I'm going to begin by facing the end of the rod off. You see, if the rod is crooked on the end, when I try to start my drill into it, there's no telling where the drill is going to go. But if I've machined the rod off so it's accurately flat on the end, I can tell that the center drill will start accurately on center, and when I do the drilling, everything will stay straight. It's little differences like this that can mean the difference between a thread that is really accurate and true and one that runs in a position where you don't want it to go. It only takes a moment to face that end off. Now I can move the carriage up out of the way, because the next part of the operation I'm going to do from the tailstock drill chuck. You'll notice that I already have the drill chuck on the tailstock, and I'm going to put a center drill in there to get the hole started accurately. bring the tool in close, secure the tailstock in position. Once again, put a little cutting oil on the tip of the drill and on the surface of the work. Notice how evenly and steadily the drill starts into the work. This is because we've been through the procedure of alignment, and we have the two ends of the lathe exactly on line with one another. It makes the starting of the drill very, very simple and very accurate. Now I switch over to a number 21 drill, which is the appropriate size for a pilot drill on 1032. You see how straight my twist drill starts, right on the axis of the work, and I can keep drilling to the desired depth. Now my tailstock ram has a calibration inscribed on the top of it, which I don't believe you'll be able to see in the picture, but there are calibrations along here, so it's marked out like a ruler, and by watching those I can tell when I've drilled the hole deep enough. In this case, we're having to drill to a depth of a ½ inch because we need a thread that'll be long enough to take a short screw. Withdraw the drill frequently so that the chips can clear from the hole, and use a little more of the cutting oil on the surface you're cutting. Now I've drilled the hole to a depth of a ½ inch so I can shut the lathe down, get rid of the chips, and I can see that I have a nice clean hole drilled in the end. At this point I switch over, I remove the twist drill, and I'll put a tap in. The metal that I'm cutting is a fairly hard steel, so I'm going to use a tapered tap. Taps come in taper, plug, and bottom. Taper has the longest taper. They're the easiest ones to start. The plug taps have a shorter taper to them. They're a little bit harder to start, and the bottoming taps are intended for running threads very close to the bottom of the hole. We don't have to get that close in this case, so I'm going to start it this way. Now I go through the same procedure of freeing the bull wheel and putting the back gears into mesh, and I have my tailstock locked to the bed. So now all I have to do is advance the ram so that the tap begins to enter the hole, and I make the same sort of movement that I did when I was cutting the external thread. With my right hand I'm keeping a little pressure on the ram. You can see that the ram is moving forward. With my left hand I'm slowly pulling the machine over so that I cut the thread and begin to get the tap going into the hole. This is a job where you need to feel for the bottom, and I don't like to keep the tap in the tailstock all the way in. I prefer to remove the tap from the drill chuck, and slide it back. Now I can put a little handle on the tap, which gives me more feeling in my hands. I can tell better what the cut is doing. But I've ensured that the thread started axially with the work. And as I turn it now, I can break the chips, and I can advance the cut a little farther. And I can keep doing that. And as I wish to, I can back it off so that I remove all of the chips from the tap. And I maintain a little cutting oil in the hole. And once again, I've ensured the accuracy of the job by being careful how I aligned my lathe. I know that I have a thread that's cut inside that rod, which is exactly on the axis. And there it is, one further step in doing accurate work. The drilling that we just did for tapping the thread into the end of the workpiece was done with a twist drill. And we worked from a chuck held in the tailstock of the lathe. The chuck that I have in the tailstock is capable of holding a 1/2 inch diameter drill as its maximum size. It can hold any of the drills that I have in the fractional set. It can hold any of the number size drills, and I have a variety of those. In the picture you can see that I have some very small ones. These are run from number 60 through number 80. I keep a stock of all of the number size drills from number 1 through number 80. A number 80 drill is only 13.5 thousandths of an inch in diameter. I can use any of these, or I can use the letter size drills, which are quite convenient as reaming drills. Any of the drills that I can use have to be with a 1/2 inch size maximum to fit the chuck. There are several ways that you can get drills. In addition to the set like I was just holding, there are reduced shank drills like this one. This is a drill that will also fit the chuck. This drill happens to be 13/16 of an inch in diameter, but because it has the reduced size shank, I can put it into the chuck and I can do good drilling work. Now this will work for any piece where I have to drill a hole in it, which I can get centered on the headstock. The workpiece can be held in a collet, as we did when we cut the thread, or it can be held in a chuck, 3-jaw chuck or 4-jaw chuck, or it can be held on the faceplate. Any of these procedures will work. In addition to using reduced shank drills, there's another way that I can work, and that's without using any chuck at all, because I have some drills that have tapered shanks like this one. The shank of this drill is a number 2 Morse taper, and I can put this directly into the socket on the tailstock and drill directly from it. You see that goes right in. It's right on the lathe axis. This provides a very accurate means of drilling oversized holes. Drills are available with taper shanks in smaller sizes, but because of the accuracy of chucks and because the drills are a little easier to obtain with the standard straight shanks, those are the type that I use for the most part. I keep these taper shank drills to be used when I have some unusual large job. The Morse tapers that are used in the tailstock of the lathe and in the headstock are usually different sizes. The Morse taper drills that I showed you to go in the tailstock had a number 2 taper, but such drills are also available with a number 3 taper, which are usually larger size drills, such as this one, and they can be put directly into the headstock of the lathe for drilling anything on the lathe axis. They fit right in, and they fit snugly in place. You give them just a little gentle tap, and you have a drill that's rotating right on the lathe axis. This is a very true mounting. This is a 1-inch diameter drill. It's a very accurate mounting for the drill, and as long as your lathe is lined up in the way that we've shown, you can do some very creditable work with it. This is a smaller size drill, but again it has the number 3 Morse taper shank to fit right into the headstock. Drilling in itself by means of twist drills rarely produces an accurately round hole. They look round to you, but if you get around to measuring them, you find that they're actually some sort of a polygonal shape, and normally the axis of the hole has a little run to it. It follows sort of a helical pattern. So when you want to true a hole up, if you need a really accurate bearing hole or something of that sort, you normally finish the hole with a reamer. Now I have 2 reamers here. This reamer is a carbide tipped reamer. This one is a plain tool steel reamer. Either one will do a good job. And you normally will want to mount the reamer in the tailstock drill chuck in the same way that you mount a drill. And you put the reamer into the hole after you've drilled it. Now when you drill a hole to use a reamer on it, you don't drill the hole quite to full size. In other words, if you're drilling a 1/2 inch hole, if you want to ream a 1/2 inch hole, we have a 1/2 inch reamer here, you'll drill the hole at a little undersize, maybe a 1/64 of an inch undersize, whatever is a convenient close size to it. The reamer should only remove a few thousandths of an inch of metal. It doesn't remove a lot of metal. When you do the reaming, it's a rather heavy cut because the reamer has usually 8 flutes, sometimes 6 flutes, sometimes 4, depending upon the size. You want to use a lot of cutting oil, and you want to slow the lathe down. You don't want to run it as fast as you do for drilling. When you begin a reaming cut, you want to keep the reamer in motion. You should never allow the reamer to come to rest, because if the reamer stops while you're making the cut, it's guaranteed that you leave some sort of rings inside, and if you want a really smooth bore for a cylinder or for a bearing or something, you don't want the rings to be in it. So when you use a reamer, slow the lathe down, work only on axis, keep the reamer moving, and keep it plenty flooded with cutting oil. When you're mounting workpieces in the lathe and you're using a chuck for it, the easy way is to grab the 3-jaw chuck and put the work in it, and it's self-centering. If you're grabbing hold of a hexagon rod or a round rod or something, it'll come down, it'll be about on center. Won't be perfect unless you have a very good chuck. But what do you do when you get an irregularly shaped workpiece like this one? In this piece, you can see the scribe lines where this round hole has to be bored into it. It's off-center. The workpiece is irregularly shaped. Clearly, there's no way that it can be gripped in a 3-jaw chuck. It has to be held in a 4-jaw chuck or on a faceplate. But how do you get such an irregular piece into position? As you examine the picture, you realize from the positions that I have the chuck jaws already located, I have it approximately in position. You see, I've placed the scale across the workpiece, and by eye I've been able to sight, and I've got these 2 jaws in approximate position so that the scribe line here is across the center of these 2 jaws. Then by turning my scale across these 2 jaws from either side, I can compare it to the scribe line, and I can adjust these 2 jaws into position. Now the work is still not accurate. This is only an approximate position, but I have the jaws roughly set out so that as I put this on the lathe, it's going to be a little easier for me to put it into position. Now I'm going to put that on the lathe, and I'm going to show you how to use the tailstock to get the work centered up quickly. Now I've mounted the 4-jaw chuck on the lathe spindle with my irregular workpiece in it, and as I rotate this slowly by hand, you can see that I have it fairly close to center already, simply by virtue of having used my scale and approximated the positions for the chuck jaws. Now this is not perfect, but I'm going to bring the tailstock forward, and I lock it to the bed. Where the lines intersected, where the center of the hole was, I made a punch mark with a very sharp little punch, and I bring the tip of the tailstock center into place on that punch mark. I slack off on each jaw just a little bit, now I run the ram forward so there's just a little pressure holding the workpiece in place in the chuck. Now you notice as I rotate the workpiece, the punched mark is very close to being on center. All I have to do is go around and tighten each jaw just a little bit. Now I'm not tightening them hard at this point, I'm just barely bringing them into position, because I'm not going to accept this as being an accurate position just yet. What I'm going to do is slide the tailstock back, and I'm going to remove the center point, and I'm going to put my drill chuck back in, because we're looking for the last word in accuracy on this. We're not going to accept anything except the best. Now I have a little center finder that I'm going to put into the tailstock drill chuck. This is a little piece, it's a wiggler that I made here in the shop myself. It's a very simple device to make. It's spring-loaded. I grip it in the chuck by this part, and this part has a tip on it which will be mounted, which will enter into the hole that I punched in the workpiece. I put this in place, tighten the chuck down a little, bring it forward, and then I very carefully guide the tip so that it just enters. Now as I turn this over, the wiggler will move in accordance with this center punch spot. Now I'm going to put the indicator on, because the movement of the tip of the wiggler is very slight, so I'm going to check it with the indicator. As I run the indicator into position, I'll bring it in to where it just begins to contact the tip of the wiggler. And I set the dial to 0. Now as I rotate the workpiece, you can see that the hand of the wiggler moves a little bit. At the present time, we have the whole operation within about 20 thousandths of being accurate. As the workpiece is off-center, as it comes in this direction toward the indicator, the needle goes up. As it moves away, the needle drops back. So at this point, what we have to do is make adjustments in the chuck jaws so that the workpiece will sit straight. At this point, we've located the spot where the workpiece is closest to the indicator. At this point, it's the farthest from it. So we loosen these jaws slightly. And we'll tighten the opposite jaws a little. This is a slow process that you take just a little bit at a time. Now if you notice the indicator movement, we've already reduced it to just a very small reading. I'm going to run that in just a little farther, and I'm going to reset my 0 mark. Now as I bring the work around, this is the spot where the work is farthest from the indicator, so I loosen these 2 jaws. And I tighten the opposite 2. And you see at this point I have absolutely no deflection on the needle, which means that I have the workpiece set exactly on center. So now let's bring the indicator back. And we'll withdraw the center finder, move the carriage back out of the way. And as I turn that over by hand, you can see that circle is rotating concentrically. And the center point which I had punched is exactly in the center of rotation. You see there's no wobble at all to that. Now that only took a few seconds to set that up, but that's a very irregular workpiece. This is the way you can work with any workpiece in which you can punch a mark for some operation such as drilling or reaming or boring, or if you can simply locate a point where you need a hole or some other feature to be machined. You could use this method to locate the center and accurately line a piece for machining a register or to make a bore hole or something of the sort. But this is a way of getting great accuracy out of your lathe as long as you recognize how to keep the lathe on axis and how to get your work on axis. Now that we've been through the procedure of doing accurate turning on the lathe and aligning everything, we know how to turn a very accurate straight cylinder, and we know how to turn a deliberate taper if we want one. The question comes up next of how do we hold a workpiece such as a wheel or a gear or something that has a drilled or reamed hole in the center. The best way to hold it is on a mandrel. Mandrels can be made in a number of different ways, and I'm holding one of the small simple ones in my hand. Commercially, mandrels are very often made as split mandrels. They're quite expensive to buy. They're not so easy to make, and frankly, there are other mandrels that you can make in the shop and do your work just as accurately and with a lot less expense and a lot less effort. When you put work in a lathe, the most accurate way you can position it is to put it in a collet. So the mandrel that I've made here was made in a collet, and when I use it, I return it to the collet in order to do accurate work with it. It has a 3/8 inch diameter shank. It has a 1/4 inch diameter surface, and on the end it has a 1/4 inch 20 thread. With the thread I can put a nut on the end so that I can put a wheel or something of the sort that has a 1/4 inch diameter central hole. The nut will hold it in place. Once I've put the piece on the mandrel, I can put the mandrel in place in the collet and tighten it up, and I know that this whole thing is going to run true because I machined it in this position with my lathe accurately positioned to give me a straight cylindrical turn. The nut will hold my workpiece, and whatever turning or machining operations I have to do on it can be done accurately. I've also center drilled the tip of this mandrel so that if I want to, I can bring up the center in the tailstock to support the outer end, which helps to improve the rigidity of the mandrel while I'm working on it. If I had wanted to, I could have machined a slight taper into this holding surface on the mandrel. Not very much, maybe a 1/2 of an inch taper from one end to the other. That is smaller at the outer end and larger at the inner end, so that when I push the wheel onto it, the natural taper of the mandrel would secure the wheel in position. I personally don't like to use tapered mandrels because it's more difficult to withdraw the work from them when you've finished. I find that a straight cylindrical mandrel of this sort with a small nut holding gives all the holding ability that I need. Now, running in the collet is a good way, but running on centers is also a very good way. I have another mandrel here, which is similar to the one that I just showed you. This one has a very rough 1/2 inch shank on this end, but that shank is not used to align it in any way. This particular mandrel has a center drilled hole in both ends, so that when I want to use it, all I have to do is put a lathe dog on it and tighten it up, and this little mandrel mounts between the lathe centers. The headstock center goes in this end, the tailstock center in this end. Now this one, I've turned 2 different steps on it, which means that I can put 1/4 inch work on this end, I can put 3/16 inch work on this center part, and they will both hold accurately. You can see that along this area I have milled a flat spot. The reason for that is that I can tighten set screws down on it, that if I'm machining some kind of a little wheel which is to be held in place in the machine by means of a set screw, I can put it on this mandrel, tighten the set screw, put it between centers, and I can do all of the machining work on it. The mandrel that I have here is also similar to the one that I just showed you, but this is a much larger size. This one mounts between lathe centers. You can see that it has a center drilled spot in this end, and it has a center drilled spot in this end. I always put this one between centers because I made this one for quite heavy work. It has an area turned down in this spot which holds the work. This one I custom made for making gears. These are the gears that I use in my lathe, and I've always machined them on this mandrel so that I get them accurate. I hold them in place by putting on a washer and a nut. In this position. When I tighten that down, it's held very securely. And the way that I use this is that I will begin by putting on here a piece of metal which has a central hole drilled and reamed to the correct size that I'm going to use in my lathe. I put this between centers on the lathe, take a turning cut to bring the outside diameter of the gear to exactly where I want it. Then I proceed to index and cut the teeth and wind up with a gear which I can use in the lathe. The important point of using mandrels is that they allow you to hold the work in an accurate position so that when you turn this outside, you know it is absolutely round and you know that it's absolutely concentric with its central hole. If I were to take a facing cut or to do some sort of an undercut, I would have that same assurance that I preserve the roundness and the accuracy, the center register of the workpiece. In order to conduct milling operations on the lathe, it's necessary to have some way to support the milling cutter, which you can do with collets or end mill holders, something of that sort. But it's also necessary that the work be supported. I've put a vertical slide on the lathe. It mounts in place of the compound slide, and such a slide is available from virtually every lathe manufacturer. It's important when you set it up to have it set in a position where it will be accurately placed in order to do accurate work. And you can see that I've put an indicator in a collet on the lathe spindle, and I've put the milling slide, the vertical milling slide, in its approximate position on the cross slide. Now the base of the milling slide has degree marks around it, and you can line this up about the same way that you do with lining up the compound rest. But the question that comes up is, how accurately are you doing it? This is the same situation that we had when we lined up the compound slide. The degree marks are good, but they're not perfect. Now I've put it approximately in position, and we'll watch the indicator, and we see that it's moving just a little bit. It's not out a great deal. We'll bring it back, and we'll gently tap it. And we test it again. This is a process similar to what we went through in lining up the compound slide. We were getting it quite close now. There it's quite good. It's not moving. There's a little blip because apparently there's a little nick or something in the surface of the milling slide jaw. I'm going to tighten this in place by tightening down on the two screws that clamp against the circular dovetail, but I'm also going to put a packing under here, and I'm going to put one extra screw to hold it in place. This screw will apply pressure at the back of the vertical milling slide, and it prevents it from moving. Now I can move this back out of the way, and my slide is ready to move. You see, by turning this handle, I can run the slide up and down within a limited amount of distance, although you don't want to go too far with it because you don't want to disengage your dovetail. You want to keep within a reasonable distance of the center position. By loosening the big nut back here, I can tip this head to different positions, and of course I don't have to align the vertical slide in the position I have it here. I could turn it at an angle, I could turn it at 90 degrees, but this is the most useful position in which you can mount the vertical slide. The work pieces are mounted in here. It has prismatic jaws that come with it, and they permit you to hold round rods or other shapes. This type of milling cut is best used for cutting key slots in shafts and for taking milling cuts across the edges of work pieces. Now that I have the vertical slide indicated into position so that I have it accurately aligned with the cross axis of the lathe, I'm ready to begin a milling cut. And I've placed the workpiece that I'm going to mill in the jaws of the slide. What I'm going to do is mill this face off to make it nice and straight. Now, a tool that's very useful for doing that is a fly cutter like this. The fly cutter has a plain shank, and it can be held very well in a collet. So I've put a 1/2 inch collet in the lathe, and I'm going to put the fly cutter in place. I tighten it up so that it's held securely, because this is a very important point. There's a lot of stress to the cut. I would like you to notice one other thing, and that is that I've put a dial indicator toward the tail end of the lathe with its contact point against the carriage. This is the way that I'm going to measure how deep I'm making my cut. As I bring the carriage forward, you'll see the dial indicator move, because this shows how much the work is moving toward me. As I move it back, you see the dial indicator move in the opposite direction. This is one place where a long travel indicator is necessary. Now I'm going to bring the tool around so I can see where the cutting point is, and I'm going to move the workpiece across so the work will come over it, and I'm going to bring the carriage forward so that it just begins to contact the work. Now at this point I'm going to set my dial for 0, because this is going to be the starting point of my work. This is the way I'm going to measure it. You see, the lathe has no means of measuring the position of the carriage otherwise, so I have to provide something for it. The lathe is a very good way to do this work, but it doesn't have all of the provisions built into it that a milling machine does. Now you'll notice that I've brought the height of the workpiece up so that it's on the center line of the lathe, that the center line of the lathe comes right across the middle of the work. And this is the way I'm going to take my cut. I'm going to lock the carriage in position because we don't want that to move. Now that I have everything accurately positioned and the tool in position, I'm going to use the cross slide to feed the work across the tool. As the point of the fly cutter sweeps around, it will begin to mill away the surface of the workpiece. Notice that the speed that I'm running the lathe is not very high. When you do milling work on the lathe, you don't run the spindle as fast as you do for lathe work of similar size. You run about 2/3 of the speed that you would run the lathe. And with your videotape, I've included 2 sheets, one of which gives the rotational speeds for running the lathe while you're doing lathe work and boring, turning work and boring, and the other gives you a set of speeds that are suitable for doing milling work. Now you can see the chips coming down, and as that fly cutter sweeps around, it's taking the surface off of the work piece. The piece back. surface is looking quite good. If I want to continue and deepen the cut, I can move the carriage forward a few thousandths. Don't try to take a deep cut because you're going to get into trouble. You remove the metal slowly. You can see the chips flying, that it's taking a second pass. Now you can see that the fly cutter took quite a nice cut across there and smoothed that out very well. Suppose you want to make a groove in that surface, a longitudinal groove from end to end. The best way to do that would be with an end mill. But when you set up an end mill, you want to set it up a little differently. The collet is quite acceptable for holding a face cutter, but when you use an end mill, you will find you'll get much better quality work if you'll use an end mill holder. This is the type of a holder that should be used for holding an end mill and taking an end mill cut. The reason is that collets are very hard tools. They have hardened surfaces. And end mills are very hard tools. A very hard end mill being gripped in a very hard collet forms a slippery surface. Under the stress of the cut, the end mill tends to pull loose from a collet. In an end mill holder, you see there's a set screw that grubs right into a little flat spot on the side of the end mill, so it will hold it much more securely. Now this end mill holder happens to have a number 2 Morse taper, so when I put that in the headstock of my lathe, which is a number 3 Morse taper, I have to put an adapter sleeve in. The adapter sleeve is just a cone which is hollow, and on the inside to take a number 2 taper, and it's conical on the outside so that it forms a number 3 taper, and this can be inserted right into the headstock of the lathe. When you mount an end mill holder in the lathe, you have to provide a drawbar. That's what this threaded rod is. It's threaded into the base of the end mill holder, and this will pass all the way through the spindle of the lathe. On the outer end, I'll put a collar which will align it accurately in the spindle of the lathe, and a nut so that I can pull this in and it will grip the end mill holder tightly. It slides in like that, and then from the opposite end I can mount the collars and washers that hold it in place. Now we can bring the work in, and we'll move the work in the same way that we did with the fly cutter. I'm going to raise the work a little bit because we want to cut near the center of the workpiece this time. And as I bring it forward so it just contacts the tip of the end mill, I can establish where my 0 point will be on the indicator. So now I can back it off and clear the work. Now as I bring it forward, I can set the end mill so it'll take a cut at whatever depth I want. And once again, I would say that you don't want to put it too deeply. Now I'm going to put a little cutting oil along the surface of the piece of work. And now I'm all ready to take my cut. You notice that the spindle is rotating quite a bit faster than I had it for the fly cutter. The reason is that this end mill is much smaller. It's only a 1/4 inch end mill, whereas the fly cutter was sweeping through about 1.5 inches or so. So we want to run it faster to get a reasonable working speed on the cutter. Now I can deepen the cut a little more. And in this way I can keep going to make a horizontal groove as deep as I want it. Now suppose I want to go with a vertical groove. All I have to do is move the carriage back a little, run into the position where I want the groove to be, and now I'm going to use my vertical slide. See, we come right back to our 0 mark. Deepen the cut, lock the carriage in place. Now I'm using the vertical control to move the workpiece up and down over the end of the tool. Notice that I'm keeping the vertical slide near its central position. I'm not going way off because I don't want the dovetail to disengage. I don't want it to be way out where the dovetail is being weakened. The next job that we're going to do in milling is to cut a key slot in a steel shaft. Now you notice that the cutter that I have in my hand here is a Woodruff cutter. It's a circular cutter, very much like a saw. You can see the teeth on it. And it has a half-inch steel shank. This cutter, like the end mill cutter, and for the same reason as the end mill cutter, I mount in an end mill holder. In order to put this in the lathe, I'll use the reducing sleeve because this is a number 2 Morse taper also, and I'll put it in place with a drawbar just the same as I did with the end mill holder. There I have the drawbar screwed into the end mill holder with a Woodruff cutter in it, and I'm going to slip this into place in the lathe spindle. Now you want the key seat to be centered on the shaft, so you run the shaft forward by moving the cross slide, and then by looking down from the top you can get the alignment, and once you have it in position you'll lock the carriage so that it doesn't move. In this setup, I don't have to use the indicator because the depth of cut is going to be controlled by using the vertical slide and bringing it up in this fashion. The feed of the cut will be taken by using the cross slide. The cutter will rotate in this direction. So what I will do is feed the work in until I get to the depth where I want the groove to begin. Then I will raise it so the cutter begins to cut, and then I will bring the cross slide back in order to make the cut. This is because when you take milling cuts, you always want the work to travel against the direction in which the cutter is rotating. If the cutter were to rotate in the other direction, then I could feed the cross slide in to make this cut. But because of the direction of rotation, I make the cut as I withdraw the work. Now I want you to notice one thing as we set up this shaft in order to cut a key seat in it. I have 2 prismatic bars which are a part of my vertical slide. When I put the shaft between them, they provide a good flat clamping surface so that when I put it in place and tighten the bolts down, it will be held securely. The cutting of a key seat in this way is another fairly heavy cut, so you want to be sure that everything is good and tight while you do it. Once it's in place, you can move the carriage back and forth. To get it aligned on the center, because we want to cut the key seat in the center of the shaft. Once you have the position, lock the carriage where you want it. Now we can gently raise the vertical slide, because this is the way we're going to be feeding the tool to the work to the tool. And we bring it into its approximate position. By hand you can just pull that over to see that everything is okay. Now you want to put a little cutting oil on the surface where you're going to be cutting. And now you're ready to begin the cut. Now I can raise the vertical slide by turning the handle on the top of it. And it has a collar on it marked in thousandths of an inch, and this is how I'll gauge the depth of the cut. You see the tool is just beginning to contact the work now, so I'll advance it so that I'm taking a cut of about 6 or 8 thousandths of an inch deep. And as I bring the workpiece back slowly, you can see that the Woodruff cutter is beginning to cut the groove. Don't try to take away too much metal at a time, because this is quite a heavy cut in steel. Cut's coming very nicely now. I'm going to put just a little more cutting oil into it, beginning to get dry. It's looking very good. Now you can see what a nice clean little key seat we cut in there. In some respects, American lathes are built a little differently from European lathes. I've taken the compound rest off of the south bend, and you see there's just a very small table area that's really not very useful for anything. Many European lathes have a long slide built across here that has T-slots in it, and that's a very useful item when you're wanting to do milling on the lathe. And what I've done is to make up a table which I can put on the cross slide. It has a round dovetail on it which matches the socket in much the same way that the compound rest does. And when I put this in position, I put a parallel between, and you see I'm comparing that edge to the faceplate. So with just that simple movement, I've aligned that table in a very straight position on the cross slide. Now I tighten it down so that it can't move. I back it up and tighten the opposite side. Now this provides me with a very nice surface which I can attach work to. One of the things that I can do with it is to place a milling vise on it. And I have holes on the table where I can attach clamping studs so that I can put the milling vise in either position or if I need to, I can mount it at an angle. And the milling vise allows me to hold work for taking milling cuts that are within keeping of what the machine can handle. What I mean by that is that I have no vertical travel. I'm restricted now to moving in this direction or moving in this direction, so that I can mill anything that I can place where it will be on the lathe axis to coincide with the cut. I can make some provision of moving up and down in the vise jaws, and whatever I do with it, I will have a solid mounting. I can also use an angle plate, such as the one that I have here. This is an accurate angle plate which can be mounted in this position or in this position or anywhere between. And this is another case where I can clamp the angle plate securely to my little milling table, and if I can position work on this table which to coincide with the lathe axis, I can take whatever milling cut I need with an end mill or with a fly cutter or whatever. Of course, in doing this you have to be careful, because you will have studs sticking out, some sort of clamping, or perhaps clamps gripping it, and you have to be careful so that you keep the clamps clear of the cutting tool. So far, all of the milling cuts that we've talked about have been taken by using the spindle of the lathe and mounting the work in some way on the carriage. But there's another way that you can take milling cuts, and that's to put a little milling head mounted on the cross slide in some way. I have a vertical column here which allows me to move this milling head up and down. It contains its own motor, and I can mount a cutter on it. As I move the carriage back and forth, I get one direction of travel. As I move the cross slide in and out, I can control the depth of cut. And as I move this handle up and down, I can control exactly where the cutter comes. So I've completed all the things that I need for doing good milling, and that is 3 directions of control. This unit has its own separate motor, which powers the cutter. This is a setup that I use for cutting gears. We've completely reviewed this process of gear cutting in another videotape in this series. And it does not have to be restricted to gear cutting. There's no reason that I can't put an end mill in this milling head and use it with an end mill or with a fly cutter or with any of the other forms of milling cut that I can take. The important thing with this is that the work is supported by the lathe chuck or by the lathe centers or something of the sort. You see there I have an end mill held in an end mill cutter, which can do the same type of work. In this case, I could bring this up higher so that I could run the tool in, and I would be able to take a cut across the top of a workpiece or whatever. I could mount between centers or in a chuck. The clearances are not quite as liberal as they could be, so you have to watch where you're cutting so to be sure that you don't hit into the chuck. If you have a chuck up here, you have to be sure that your work is mounted so it clears the jaws, or if you put it on a faceplate, you have to be careful that you don't hit against the faceplate. The lathe makes an excellent machine when you have to do a boring cut. You can use a small boring bar mounted on the tool post, which is a fairly fundamental form of boring. In fact, in the tape in this series, which deals with the fundamentals of machine lathe operation, I detailed how to make a little boring bar holder and the boring bars to use. You can also work from a micrometer boring head, or you can do a form of boring which is called between centers boring. The boring bars that I use for doing boring between centers are like these. They're plain steel rods which you can make for yourself. They have one single cutting tool which is located near the center. Each end of the boring bar has a center drilled spot in it so that you can mount it between the lathe centers and run it very solidly. I have different size bars because they're different cuts that I take. A very thin one like this I might use for line boring a set of bearings. One that's a little heavier like this I might use for boring small cylinders or bushings. A large one like this is normally what I will use for machining a fairly large cylinder for an engine or something of that sort. In order to do good boring with the bar between centers, you have to position your work accurately on the lathe axis, and you have to clamp it in place in some way. The boring table that I was showing you before, which can be used for milling work, is a very useful accessory for doing this type of work. I have a bushing mounted on here which I have to bore out. I've clamped it in place because I can screw studs into my table, and I've put it on a large V-block which will hold it in place. You notice that I have some thin steel shims underneath of it. These are put in place so that they can raise the bushing up to the proper height so it's on center where I need to bore it. The way I set this up is to use a lathe dog on one end of the boring bar so that it goes on the center, and the dog engages the catch plate, and then I bring up the tailstock center and lock it in place. Now as the lathe rotates, you can see how the boring bar is turned on centers, and this makes it a solid tool which will take an accurate cut. This is the most accurate form of boring that you can do on a lathe, and the lathe becomes equivalent to a boring machine when you set it up in this way. I recommend that you use power feed for the longitudinal movement of the carriage. You see your workpiece is clamped on the carriage and will travel with it as this tool rotates and bores away the center. Use the longitudinal feed function of your lathe to get a smooth feed rate. I'm advancing the carriage now so that I'm bringing the shoulder inside the work very close to the tool. Now with the boring bar mounted between centers and the dog engaging the catch plate, I'm ready to put the power feed on so that we take the boring cut. The single point tool that's in the boring bar is shaped the way a plain lathe turning tool is shaped, except it has to have enough clearance at the heel to be sure that it doesn't rub inside the hole as you bore it. I've engaged the power feed, and as the carriage advances, the rotating tool will begin to cut inside the hole. You can begin to see the chips coming out now. When you're taking a boring cut like this, it's essential that the clamps be holding the workpiece very securely. This is why I have it in the V-block so that it can't slip. It's also a good idea to tighten up on the gibs in the cross feed so that there doesn't come a back and forth motion. If you let the cross slide loose, it has a tendency to work under the stress of the cut. It's a rough casting so that it's not a uniform wall thickness where we're cutting. That's why you can hear the unevenness to the cut. Now the tool has come all the way through, so I can stop the carriage and stop the lathe. I'm going to back this off. It's just packed full of chips in there. You can see the surface inside where the boring tool cut. I made a nice finish. This was only the first cut, and we took a heavy cut. If you want to get on to a smoother surface or a larger size, you advance the tool and carry on with it. I want to show you the tool so you can see the shape of it and the way we adjust it. You see, here is the lathe tool. It's shaped like a round-nosed tool that you would use for turning, but it has to be made short so that it will fit inside the work. And there's a set screw here that I use for adjusting it. If I had wanted to increase the diameter of the bore that I just made, I would have loosened the set screw and pulled this tool bit out a few thousandths of an inch and retightened it and run the bar through a second time. In any event, it's the most accurate form of boring that you can do on a lathe. This is the way that I prefer for machining the cylinders for engines in particular. There's one operation that you can do on a lathe that provides a great deal of accuracy, and that's a grinding operation. Now, grinding operations are messy operations because they throw a lot of abrasive particles around, and whenever you're grinding, you want to be sure to put the things over your lathe bed to protect it. The tool that I have mounted on the compound rest here is a little tool post grinder which was made in the shop here. It carries a stone on this end. The stone rotates in this direction. I can change the stones to different diameters. I can change to little small ones. But the purpose of using this grinder is to take any hardened surface and grind it away so that you leave it with great accuracy. Now, the center points that are used in a lathe are hardened, so these are good subjects to use for grinding. They don't have to be the pointed shapes. You can grind along cylinders, or with little tiny stones you could reach inside and grind on the inside. There are a whole lot of things that you can do. But for the purposes of the demonstration, I'm going to show you how I grind a center point. I've taken a number 2 Morse taper center point, which would fit the tailstock, and I've put it in a sleeve so that it fits into the headstock, which is a number 3 Morse taper. Now, the included angle on the point of a center is always 60 degrees. So in order to accomplish a 60 degrees, I'm going to turn the compound slide to a 30-degree angle, which I can check from the protractor on the bottom, or I could use an indicator to indicate it into a very accurate surface. The stone rotates in this direction. I want the lathe to rotate in the opposite direction because I want the work on the lathe to go in this direction past the stone, which is coming in this direction. We want them to be rotating against one another. And we take a very light feed and we use the compound rest handle to move it back and forth. Now I'm going to clamp that into position and show you how I do that. I've got the compound rest turned to a 30-degree angle, and I'm going to lock the screws that hold it in that position. You see, this little tool post grinder has its own motor built into it. It's belt driven down to the spindle, which carries the stone. Now as I bring this forward, I have to feed the compound slide in. I have to feed the cross slide in. And then I have to come forward with it, because I have to get it in a position where it will just clear the surface of the center point. Now I'm placing a towel so that the hard abrasive particles from the grinding don't get onto the lathe any more than I can help it. Now as I bring this back, the stone will be brought into contact with the point. I'm checking the travel to make sure that it covers the full length of it, and it does. Now I'm going to run the lathe backwards so the spindle turns in that direction, because the grinder will be turning in this direction. Okay, shut down while I start her up. Now this center point was in quite good condition before we started, so it took very little grinding of the surface to bring it back to a really good surface. It's accurate now, it will hold work very well, and it has a good running surface on it. The grinding can be applied to anything where you want very fine accuracy. Usually you grind on hardened steel is where you get the very best results. It can be used, for instance, in grinding valves or in grinding the stems of hardened valve pushers, that type of thing, where you can get a very precise control of the diameter and you get a very good surface and you can produce very accurate work, which has been the theme of what we've talked about today, to try to set your lathe so that everything you do will contribute to accurate work. And just bear in mind that the work that you produce on your lathe can certainly exceed the accuracy that the manufacturer put into the lathe if you apply the principles that we use today and work carefully. And I think that you'll find as you apply logic to each lathe job and think it through and apply the principles, you're going to find that you enjoy your lathe work even more than you do right now, because you'll see the fruits of it in getting finer work and better fitting pieces.